Hello, I'm Lewis, and I'm a member of the Oxford Protein Informatics Group. We're based in Oxford in the UK, and there I'm supervised by Professor Charlotte Dean, who heads up the group. Thank you very much for stopping by my poster. I'm also giving a longer talk as part of the 3D SIG COSY, so if you want to look at this research in more detail, then please do check that out. Alternatively, you can also find our preprint, which is on bioRxiv, and you can find this information also by scanning the QR code at the bottom of the screen. So as part of this video, I'm going to skip over the intro. You can find this information in my talk, or you can simply download the poster as a PDF. And I'm going to jump straight into the methods and the results. So first off, let's look at the methods. So I'll get the laser pointer up here. So looking at step one, the first thing to note is that Paragraph is trained on both crystal and model structures. The reason why we want to do this is because we want our paratope prediction method to perform well on model structures. And this hasn't been emphasized enough in previous literature. The reason why we want this is because in most research settings, we simply won't have the crystal structures available to us, and they're expensive and time-consuming to obtain. So we really need these structure-based prediction methods to work well on models. So what we do is we take the PDB files of our crystal and model structures, and we create a very simple graph representation. So what we do is we take the C alpha atoms of each residue in the CDR loops, plus or minus 2 residues on either end, and we represent these as nodes with the coordinates given by the 3D coordinates of these C alpha atoms. Now that gives a structure of our graph. Then associated with each node is a very simple 22-dimensional feature vector, which consists of a one-hot encoding of the amino acid type and a one-hot encoding of the chain ID. Is that a heavy chain or a light chain? One key thing to note here is that the reason we focus on the CDR plus or minus 2 is because we found that when training over the entire variable region, the entire FV, we found that the high class imbalance of 10:1 between non-binders versus binders, that really made our training quite unstable. And so we chose to focus on the smaller search area during the training step. We then take this graph representation of our antibody, we feed it into a series of 6 equivariant graph neural network layers where nodes that are close to one another in space are able to learn more about its neighbors. And we use a 10 angstrom distance cutoff for this. We then collapse this 22-dimensional feature vector, which is output by our graph layers. So we utilize skip connections there so the dimensionality doesn't change. We collapse this 22-dimensional feature vector down to 1 dimension, which is the binding probability for each residue within our CDR plus or minus 2. Now, to compare to other existing methods, we then expand our predictions over the entire variable region by predicting 0 for all residues that aren't in the CDR plus or minus 2. This very simple expansion works really well because only 1% of these other residues are actually classified as binding. And we can see then that we end up with a good prediction of the paratope, which seems to be at the center of where this antigen is bound. So that's one of the great things about Paragraph. It seems to learn more about that context. But one of the limitations is we don't necessarily pick up these 1 or 2 binding residues that sit outside of the CDR plus or minus 2. It's also worth noting that the prediction itself is very quick compared to other leading methods. Jumping down to the results now, we have compared the performance of Paragraph against a very simple baseline which we put together and 3 other recent paratope prediction methods. I won't go into them in detail, just very quickly. Pecan is the current leading paratope prediction method. This uses a more complicated 62-dimensional feature vector. It uses graph convolutional networks. It uses the antigen for attention, and it utilizes transfer learning from general protein-protein interactions. So using a simpler architecture and simpler feature vectors, we do actually exceed the performance of Pecan using our chosen metric of the PRAUC. And the reason why we choose to focus on the PRAUC here is because our baseline shows that the ROC AUC can very easily be hacked, where our baseline is simply looking at the proportion of residues that bind to each sequence position in our training set and predicting that very same proportion for our test set. So we really do need to focus on the PRAUC here. A couple of final things to note are that the performance of Paragraph does improve when we provide it with more data. So our expanded dataset contains around 2.5 times as much data as the Pekin dataset, which is the dataset which all of the other results are provided on. And really promisingly, our performance improves with model quality. So the tool that we use to predict our structures, our blooper, alongside the predicted structure, it also outputs a model confidence. And what we find is that the accuracy of our method improves with model confidence, and this is useful in 2 ways. One, as the antibody structural modeling improves in the future, we should get improved paratope prediction performance for free, which is fantastic. And then the second point, which is useful for right now, is that the model confidence score can also provide a proxy for the paratope prediction confidence as well. If we have a good structure, we hopefully do have good paratope prediction as well. Well, thank you very much for stopping by my poster. I am going to be in Madison in person if anyone does want to come by and chat. Thank you.